Sony just dropped a $700 PlayStation. $700 for a console, and the wild part? If you put it next to the regular PS5, they look exactly the same. No shiny Pro badge, no glowing neon strips, no sleek redesign to make it feel futuristic, just two big black and white boxes that could pass as twins. One costs $500, the other costs $700, and unless you're some kind of silicon psychic, you'd never know which is which. Now that makes you wonder, why would anyone pay $200 more for something that looks identical? Well, because all the magic is happening under the hood. Sony didn't bother with flashy cosmetics. They poured every dollar into what you can't see. It's like buying a car that looks like a Toyota Corolla on the outside, but under the hood it's secretly packing a Formula One engine. That's the PS5 Pro. On the outside, same spaceship-looking console. On the inside, it's a whole different beast. And the heart of that beast? The GPU. That's the chip that controls everything you actually see on screen. The graphics, the lighting, the shadows, the reflections, the part that makes your jaw drop when you walk through a neon-lit street in Cyberpunk or swing past skyscrapers in Spider-Man. Sony didn't just give this thing a mild upgrade. No, they went full mad scientist. They stitched together pieces from 3 different AMD GPU families, RDNA2, RDNA3, and even some unreleased future tech. It's like they raided AMD's lab in the middle of the night and said, "We'll take a little of this, a little of that, oh, and whatever experimental thing you're not supposed to release until 2026. Mark Cerny." PlayStation's hardware wizard calls it RDNA 2.x, which honestly sounds like a placeholder name, like they couldn't decide if it was RDNA 2.5 or 3. But here's the bottom line. This hybrid design is a monster. The original PS5 shipped with 36 compute units. The Pro, 60. That's a 67% jump. Imagine if your boss gave you 67% more coworkers overnight. Suddenly, projects that used to take weeks are getting done in days. That's what's happening inside the Pro. And all that extra muscle translates into raw power. 16.7 teraflops compared to the PS5's 10.28. If teraflops sound like a made-up gamer currency, think of them like horsepower. The Pro basically strapped a turbocharger onto the PS5's engine. And here's the kicker. Sony managed this without moving to a smaller manufacturing process. They're still on the same 6nm tech as the PS5 Slim. So instead of shrinking the kitchen, they trained the chef to cook in 3 different cuisines at once. That's bold and risky. The real flex, though, is ray tracing. On the regular PS5, ray tracing is like extra seasoning. Nice when it works, but it slows everything down. On the Pro, Sony says ray tracing runs 2 to 3 times faster. Suddenly, puddles in games don't just look wet, they actually reflect neon signs in headlights. Shadows bend realistically instead of looking like fuzzy blobs. Glass looks like glass, not plastic wrap. And here's the crazy part. These ray tracing features don't even exist in PC GPUs yet. Let that sink in. If you built a $2,000 gaming rig today, it still wouldn't have some of the ray tracing tricks Sony baked into the Pro. That's wild. Usually consoles are the ones playing catch-up, but this time, Sony's leapfrogging ahead. Of course, stuffing future tech into today's silicon isn't simple. Every Pro GPU has to be tested way more brutally than regular PS5 chips. It's not just, does this thing run? It's, can it handle workloads from the future without melting down? If a chip can't cut it, it gets thrown into the reject bin. That means higher rejection rates, lower yields, and much higher costs per chip. Sony's basically running a silicon Hunger Games, and only the strongest survive. And those survivors, they're expensive. Now here's what makes this so fascinating. Sony didn't need to do this. They could have slapped a slightly larger GPU in there, called it a Pro, and gamers still would have lined up, but they didn't. They gambled. They stitched together a Franken GPU nobody else has, integrated unreleased tech, and made sure it still runs every single PS5 game you already own. That's nuts, Because normally, backward compatibility is the first thing that breaks when you mix architectures. Sony somehow pulled it off. This GPU story alone explains a big chunk of why the PS5 Pro costs so much. We're not talking about a lazy refresh. We're talking about a console that's packing experimental features no PC has, with rejection rates high enough to make accountants cry. And yet, Sony still ships it at a mass market level. That's ambition. That's them saying, we're not just keeping up with PCs, in some ways we're ahead of them. But the GPU is only part of the story, because the next upgrade, the memory, is where things get sneaky. The Pro still has 16 gigabytes of GDDR6 memory, just like the regular PS5, but here's the twist: they cranked up the bandwidth by 28%, pushing it to 576 gigabytes per second. If that sounds meaningless, think of it like this. The regular PS5's memory is a 6-lane highway during rush hour. The Pro just expanded it to 8 lanes and gave everyone Ferraris. Traffic? Gone. Data just flies. And then Sony added an extra 2 gigs of DDR5 memory just for the operating system. Why does that matter? On the regular PS5, the OS and games have to share memory like annoying roommates fighting over fridge space. On the Pro, the OS gets its own little fridge, which means your games get the entire 16 gigs of high-speed GDDR6 to themselves. For developers, that's like suddenly having a private studio instead of a shared office. More headroom, fewer bottlenecks, smoother performance. Of course, premium memory isn't cheap. These chips cost about 60% more than standard ones, and every single module goes through brutal stress testing before it's allowed into a console. We're talking Navy SEAL training for silicon. If a chip fails under pressure, it doesn't make it into your Pro. That's another reason why the console costs more. You're not just paying for memory, you're paying for memory that survived boot camp. So to recap the first act of our story, Sony built a Franken GPU from 3 generations of AMD tech, doubled or tripled ray tracing speeds, added features that don't even exist in PC hardware, overclocked the memory, and gave the OS its own dedicated space. And all of this had to be validated, tested, and produced at scale with rejection rates through the roof. That's where your extra $200 is going. And we're just getting started because Sony's real secret weapon isn't the GPU or the memory. It's something else entirely. So if the GPU is the heart of the PS5 Pro and the memory is the bloodstream, then Sony's secret weapon is like the brain. It's called PSSR, PlayStation Spectral Super Resolution. Sounds fancy, right? But what it really means is this console can cheat in a good way. See, rendering games at native 4K with all the bells and whistles is insanely demanding. It's like asking your brain to write an exam, run a marathon, and play chess all at once. Something's gonna give. On PC, NVIDIA's solution is DLSS, AI upscaling that takes a lower resolution image and blows it up so it looks like 4K, but runs much smoother. Sony looked at that and said, "Cool idea, but what if we do it our way?" Instead of slapping extra AI cores on the chip, they made the GPU itself handle the job. That's like telling your chef, "Hey, you're also gonna DJ the party tonight." Crazy, but somehow it works. PSSR can handle 300 trillion operations per second for 8-bit machine learning. That's enough horsepower to take a 1440p frame, upscale it beautifully to 4K, and still lock the frame rate at 60. And Sony spent 4 years cooking this up. 4 years! That's like half a console generation, and the reason is obvious. You can't just throw AI into a console and hope it works. Latency has to be razor thin. If pressing jump feels delayed because the AI is still touching up your frame, gamers will riot. Sony had to fine-tune this thing to deliver sharp images and zero noticeable lag. And the best part? Developers don't have to bend over backwards to use it. It's baked into the console, which means future games can tap into PSSR without building an entire separate pipeline. For you, it just means sharper graphics and smoother gameplay without even noticing the trickery. Now, all of this, the Franken GPU, the overclocked memory, the AI upscaling brain, comes at a cost. Literally. Let's break it down. The GPU alone, around $180 to manufacture. That's 50% more than the regular PS5's chip. The high-speed memory, $65 instead of $45. Add the extra DDR5 modules, the 2TB SSD, and the fact that Sony still uses liquid metal cooling, but with a more refined process because the Pro runs hotter, and you're looking at $420 in raw parts for every single unit. Compare that to $280 for the standard PS5. And that's before you factor in the $500 million Sony invested into R&D over 3 years. $500 million just to invent this hybrid GPU, build PSSR from scratch, and make sure it doesn't melt in your living room. Cooling deserves its own shout-out here, because look, the PS5 Pro runs hotter than the regular PS5. More compute units, faster memory, AI workloads, that's a lot of heat. Sony stuck with liquid metal, but here's the thing. Applying liquid metal to a chip isn't like buttering toast. Do it wrong and you fry the whole system. So they refined the process, tightened quality control, and made sure every single unit could handle the extra heat. That's why you don't see Pro meltdown headlines yet. All that precision? Yeah, it costs money too. Now let's step back and put this into perspective. $700 sounds steep, but what if you tried to build a PC with equivalent performance? Spoiler, you're not getting away with less than $1,200. Between the GPU, the SSD, the premium memory, and the cooling solution, you'd be bleeding cash. And then you'd still have to deal with drivers, Windows updates, random crashes, and the joy of troubleshooting why your brand new game refuses to launch. With the Pro, you just plug it into your TV, hit the power button, and you're in. This is where Sony is flexing. They're saying, look, we can deliver high-end PC gaming in a box for half the price. And whether you buy it or not, that's impressive. But the real question isn't can it? It's should you? For most people, the regular PS5 is still more than enough. It runs every game, delivers great visuals, and costs less. If you're a casual gamer, if you play FIFA, Fortnite, Call of Duty, you don't need the Pro. But if you're the type who notices when shadows look fake, or reflections don't line up, or frame rates dip below 60, then yeah, the Pro is for you. It's not just about playing games, it's about appreciating the tech flex behind them. Think of it this way, the PS5 is like a great mid-range car. Smooth, reliable, gets you where you need to go. The Pro is the tuned-up version with racing parts under the hood. You don't need it, but man, when you drive it, you feel the difference. And let's not forget storage. Sony ships the Pro with a 2TB SSD, because let's face it, modern games are storage hogs. One Call of Duty install and half your drive is gone. With 2 terabytes, you can finally have more than 3 games installed without playing Which Child Do I Delete Today? That's another quality of life upgrade that adds to the cost, but also to the experience. Now, let's talk rejection rates again, Waksimwe. Because this is something people don't always think about. Not every chip Sony makes actually survives the testing gauntlet. The Pro chips are held to stricter standards because they have to handle legacy PS5 games and next-gen ray tracing features. If a chip can't pull double duty, it gets tossed. That means Sony wastes more silicon, which means each working chip costs more. You're basically paying for the survival of the fittest, and this is why the Pro is fascinating. It's not just a console, it's a proof of concept. It's Sony saying, we can still innovate, we can still push boundaries, we can still bring future tech into a mass market product. Because let's be honest, consoles have been on the defensive for years. PCs are stronger, phones are catching up. Everyone's been saying, well, why bother with consoles? And then Sony drops this thing and says, because we can still do things even PCs can't. And in some ways, they're right. The Pro's ray tracing tech isn't in any PC card right now. PSSR is custom built for gaming in a way that DLSS isn't always optimized for. And all of this is packed into a $700 box, so is it worth it? That's up to you. If you're happy with the regular PS5, stick with it. It's still a beast, but if you want to see games at their absolute best, sharper, smoother, more realistic, then the Pro is worth considering. It's not a console for everyone, it's a console for enthusiasts, for the people who care about the little details, for the ones who paused Spider-Man 2 just to admire the reflections in a window, and honestly, that's fine. Not every console has to be for everyone. The PS5 Pro is like a luxury car. You don't need it, but if you can afford it and you care about performance, it's going to make you smile every time you use it. So here's the takeaway. The PS5 Pro costs $700 because it's not just another console refresh, it's a technological statement, a Franken GPU built from 3 generations, a memory system that finally gives games the full buffet, an AI upscaler tuned for buttery, smooth gameplay, and the cooling, storage, and quality control to make sure it all works. You're not just buying a box, you're buying ambition. Sony's attempt to prove consoles can still lead, not just follow. The only question left is, would you pay for that ambition? Would you spend $700 to get cutting-edge gaming tech in your living room? Or would you stick with the trusty original PS5 and wait for the next generation? You sit down, press a key, and somewhere on the other side of the world, a machine is desperately trying not to mess up the tiniest piece of plastic in your entire setup. That's the crazy part about mechanical keyboard switches. They feel so simple under your fingers, but behind every single click is a full-blown industrial process obsessed with fractions of a millimeter and fractions of a gram of force. Think about it. You've probably pressed keys millions of times in your life, but have you ever really pictured what happens before that switch ever lands on your keyboard's PCB? Before it ends up in some unboxing video with thok tests and slow-motion sound captures, that switch lived an entire previous life in a noisy factory filled with molten plastic, high-speed presses, optical sensors, and people in lab coats arguing over spring tolerances. That's the world you're about to step into. Let's start at the very beginning before there's even a recognizable switch to talk about. The story doesn't begin with colors like red, brown, or blue. It begins with steel to make the plastic parts of a switch. Top housing, bottom housing, stem. Manufacturers first need molds. These molds are blocks of hardened tool steel, and they're one of the most expensive, time-consuming parts of the whole process. Engineers spend weeks designing the cavities inside these blocks so that when molten plastic is injected at high pressure, it fills every tiny channel perfectly, cools evenly, and pops out as a precise, consistent part. If the mold is even slightly off, the stem might wobble, the housing might not close tightly, or the pins might not align with the PCB. That's the fun of switch manufacturing. If you're off by just a hair, the whole thing feels cheap. Once those molds are ready, the plastic phase begins. Huge bags of plastic pellets, often variants of polycarbonate or nylon, are fed into injection molding machines. Inside, heaters bring the pellets to a molten state, and a screw mechanism pushes the hot plastic into the mold cavities with intense pressure. In a few seconds, the channel that was once empty is full of liquid plastic. Then it cools. The mold opens. Out comes what looks like a weird tree made of tiny parts connected by thin plastic runners. Each branch on that tree is a switch component waiting to be freed. At this point, nothing looks premium. Workers or automated cutters separate the parts from the runners, remove sprues, and sometimes tumble them or lightly polish them if needed. Tiny bits of leftover plastic can cause scratchy stems or housings that don't fit tightly, so even this apparently boring step is crucial. This is where the first wave of quality control lives. Workers quickly scan for warped stems, broken housings, or color inconsistencies. If a batch is off shade from what a client ordered, say a custom lavender or deep teal designed by a popular keyboard creator, it might get rejected outright. Meanwhile, something far less visible but just as important is being created: metal components. Deep inside every mechanical switch is a simple idea: two pieces of metal touch, and your key press is registered. But getting that to happen at the right moment with the right feel is an art. Manufacturers start with long metal strips, typically made of copper alloys for conductivity and springiness. These strips go into stamping machines that punch out and form the contact leaves. The machines bend, notch, and shape each leaf so that once it's installed inside the housing, pressing the stem will move the leaf just enough to close the circuit. Then there are the springs, the unsung heroes of your typing experience. These springs are made from steel wire that's coiled with precise tension. Change the wire thickness or the number of coils, and suddenly you've created a 35-gram featherlight switch or a 67-gram heavy hitter. Now, picture this. On one side of the factory, you have trays filled with bottom housings. On another side, bins of stems in different shapes and colors. Somewhere else, boxes of springs, rows of metal leaves, maybe tiny vials of lubricant. All of these are about to be brought together on an assembly line that looks like chaos but operates with ruthless order. In a typical modern setup, bottom housings move down a conveyor or indexing table. The first station inserts the metal leaf and the stationary contact piece. The parts need to sit in precise grooves inside the housing, so machines use guides, pins, and sometimes cameras to make sure everything is aligned. If a leaf sits too high or too low, the actuation point of the switch shifts, and suddenly your linear gaming switch feels mushy or unpredictable. The assembly line lowers a stem onto each spring, guiding the cross-shaped top into position so it doesn't scratch or deform the internal walls of the housing. Then, in another station, the top housing is placed over the entire assembly and snapped into place using the small clips molded into both pieces. With a quick clack of plastic on plastic, the switch's body is sealed. At this point, what you recognize as a mechanical switch finally exists, but the journey is not over. Now comes testing. Some factories use random sampling, pulling switches from a batch and running them through keystroke machines that press each switch tens of thousands of times to ensure it doesn't fail prematurely. Others use more advanced tools, optical sensors or force displacement graphs, to measure the exact curve of the key press. How much force it takes to start moving, how much force at the bump, how sharp the drop is after actuation, and how quickly it returns. If that curve doesn't match the design spec, the batch might be flagged for issues. This is also where factory lubrication comes in for certain lines of switches. Some budget switches skip lube entirely to save cost, but higher-end or enthusiast-focused lines might have small amounts of lubricant pre-applied to the stem rails, the slider surfaces, or the spring ends. This reduces scratchiness, stabilizes the feel, and can even dampen noise. Getting this right at scale is hard. Too much lube and the switch feels sluggish or mushy. Too little and users complain that it feels sandy. Some manufacturers use micro-dispensing machines. Others rely on workers with fine tools and a lot of repetition. But lubrication and precision aren't the only secrets hiding inside a good switch. There's also the choice of plastic itself, and this is where things get surprisingly nerdy. Different switch makers mix and match materials like nylon, polycarbonate, and POM for very specific reasons. Nylon housings tend to give a deeper, fuller sound, making each press feel a bit more thocky and muted. Polycarbonate, on the other hand, is harder and can sound a little brighter, a bit more sharp and snappy, especially when paired with a firm plate and hard keycaps. Then there's POM, often used for stems because it's naturally slick and low friction, which is why so many switches feel smoother than they did a decade ago. Factories don't just pick these plastics at random, they test combinations the same way enthusiasts do, changing just one variable at a time to see how it affects sound and feel. A nylon bottom with a polycarbonate top might give one profile, while full POM housings lean in a completely different direction. Multiply that by different stem designs and spring weights, and suddenly you've got an entire ecosystem of switches born from a handful of base materials. All of this effort is chasing one simple goal: making a switch that feels good for an absurdly long time. Many modern mechanical switches are rated for tens of millions of presses, sometimes even stretching toward the 100 million mark. That durability rating isn't just marketing. It's backed by machines in the factory pounding these tiny parts over and over until they either fail or refuse to. Zoom out from one switch to an entire batch and you start to see the scale. Thousands of switches are stored in plastic trays or hoppers. Then they're counted, either by weight or by optical counting machines, and bagged into retail quantities, 70, 90, 110, or bulk packs. These bags get labeled with force rating type, linear, tactile, clicky, colorway, and branding. From there, they're packed into boxes, loaded onto pallets, and shipped out to keyboard brands, custom kit makers, or directly to enthusiasts who will film them, test them, and judge them brutally on forums and in reviews. To really appreciate how far this process has come, it helps to glance backward. Mechanical switches evolved from older typing mechanisms, early typewriters, then electric keyboards, then terminals and office machines. In those days, the focus was on durability and reliability more than feel. But as personal computers spread, brands like Cherry, Alps, Topre, and IBM introduced sturdier, more precise switch mechanisms. The classic buckling spring, for example, used a coiled spring that physically snapped as it buckled, creating a loud click and a highly tactile feel. Over time, the industry shifted toward more compact, replaceable switches like the ones we now know, modular devices where each key is its own tiny machine. What's wild today is how much customization has exploded. Manufacturers no longer make just a standard office switch. Now there are infinitely varied lineups, silent linears with built-in dampeners, mid-force tactiles tuned for long typing sessions, ultralight linears for fast gaming, and aggressively loud clickies designed more for fun than for open-plan offices. These all stem from tiny changes in the manufacturing process. A slightly different stem mold, a revised spring, a new plastic blend, or a different factory lubricant. There's also a whole world of collaboration behind the scenes. Enthusiast designers work with factories to create limited runs with unique features, long pole stems that bottom out sooner for a snappier feel, box-style stems with extra stability to cut wobble, or custom-colored housings that match specific keycap sets. On the factory floor, these custom projects might mean swapping molds, changing spring stock, and even reconfiguring lubrication settings just to deliver a slightly different feel that only a niche audience truly understands. And then comes the final transformation, the one you're most familiar with. Switches meet keyboards. In hot swap boards, switches are pressed into sockets on the PCB, their pins aligning with metal contacts that let you swap them anytime you want. In soldered boards, the pins are inserted through the PCB and then soldered permanently on the underside, creating a more secure but less flexible setup. That moment when builders press a fully assembled switch into a plate and hear it snap into place, click, feels simple. But that sound is the echo of an entire manufacturing chain that started weeks or months earlier. Consider what happens if any part of that chain fails. If the mold is slightly off, the housing might cause stem wobble and people complain about mushy feel. If the spring steel is inconsistent, some switches in the same batch might feel heavier or lighter. If the leaf isn't perfectly shaped, the actuation point can wander, making typing feel unpredictable. And if quality checks slack off, entire runs get known for leaf ping, overlubed stems, inch, or factory scratch. On the flip side, when everything goes right, a switch earns a reputation. People talk about its smoothness out of the box, its satisfying tactility, its deep thock or snappy clack. All of that starts way back in material selection, mold design, and step-by-step assembly. The magic isn't accidental, it's manufactured. So the next time you slam your spacebar in a game, speed through a late-night essay, or just casually tap through your favorite sites, you're not just pressing a lump of plastic. You're engaging a mechanical device built from carefully molded housings, precision-stamped metal leaves, tuned springs, and possibly hand or machine-applied lubricant, all put together in a factory where one misaligned fraction of a millimeter could ruin the feel you've come to love. This is the PlayStation 5, a sleek, futuristic box hiding the result of one of the most ambitious global manufacturing operations ever attempted in consumer electronics. From the outside, it's a bold, iconic design. From the inside, it's a symphony of custom silicon, thermal science, and precision robotics. The journey of every PS5 begins with the brain, a custom AMD chip forged in microscopic layers of silicon. But what truly sets this console apart isn't just what it can do, it's how it was made. Building a PlayStation 5 isn't as simple as putting together parts in a factory. It's a high-wire act that stretches across hundreds of cities, with over 1,000 suppliers, and manufacturing facilities that run with the discipline of military operations. One hiccup, one delay, one single flaw in a component, and it can cost billions. This story is about how Sony built one of the most powerful consoles in history, and how they did it using one of the most dangerous substances ever used in consumer electronics: liquid metal. At the center of this machine is the APU, the Accelerated Processing Unit. It's a custom fusion of CPU and GPU designed by AMD, based on Zen 2 and RDNA2 architectures. But this chip is powerful. Too powerful, in fact, for traditional thermal paste. In most consoles or PCs, a gray paste is applied between the chip and the heatsink to help transfer heat. But for the PS5, Sony needed something better, way better, and that's where liquid metal comes in. Liquid metal has a much higher thermal conductivity than traditional paste, which means it can move heat away from the chip more effectively. That keeps the chip cooler, the console quieter, and the performance stable even during intense gaming sessions. It wasn't an easy decision. Engineers debated the risks for months. Liquid metal, while efficient, is a finicky substance. It's electrically conductive, which means a single droplet landing where it shouldn't can fry the entire board. It's also prone to movement over time, especially when the console is standing upright for long periods. So if Sony was going to make this leap, they had to engineer their way around every single weakness. This wasn't just about slapping on a high-performance cooling material. It required an entirely new hardware ecosystem. Sony had to design a custom foam barrier to contain the liquid metal and prevent it from spilling beyond the chip's edges. That foam had to be precision cut and thermally stable. It couldn't shrink, it couldn't deform, it couldn't fail, ever. Then came the challenge of applying the metal itself. This wasn't something human hands could do reliably. Liquid metal smears, it oxidizes, it can't be handled like paste. So the solution was robotics. A highly specialized robotic arm was developed just for this task. Not borrowed from other manufacturing lines, not repurposed. Built from the ground up with one job: to apply this volatile substance with a level of care normally reserved for semiconductor fabs. The robot uses a tiny needle-like applicator to deposit the liquid metal in a perfect pattern across the APU surface. Not too much, not too little, just the right amount to ensure maximum thermal transfer while maintaining isolation from the surrounding components. It then spreads it using a technique that resembles micro-squeegeeing, leveling out the surface so there are no bubbles, no streaks, no missed spots. And this all happens in an environment that's sterile, temperature-controlled, and monitored down to the micron. Sensors constantly verify the placement, the amount, and the spread of the liquid metal in real time. If anything deviates from the target, or even slightly, the machine halts. It's that sensitive. Once the liquid metal is in place, the massive aluminum heatsink is lowered into position with robotic arms. Again, precision matters. Even pressure must be applied across the entire contact surface to avoid air gaps. Air gaps mean hot spots. Hot spots mean noise, throttling, or worst of all, failure. To ensure nothing moves during shipping, foam pads are also placed around the APU area to hold everything securely in place. This is critical because if the console experiences a hard bump during transit, even the smallest shift in the heatsink could lead to misalignment, and that misalignment could disrupt cooling. There's also a consideration for long-term usage. Liquid metal tends to settle over time. Gravity can cause it to pool unevenly, especially if the console is positioned vertically. Sony's engineers took this into account when designing the containment system. The seal around the chip ensures the liquid metal stays exactly where it's needed, no matter how the console is stored or moved. And then there's oxidation. Liquid metal can react with air or other metals, forming a crusty layer that drastically reduces its thermal performance. To fight this, Sony's system ensures the metal is fully enclosed, isolated from the environment, sealed in a vacuum-tight thermal envelope. In total, the decision to use liquid metal in the PS5 wasn't just about performance, it was about pushing the boundaries of what a home console could be. Taking something that had previously only been used by custom PC builders and integrating it into a global supply chain with millions of units in production. It was a gamble, one that paid off, because it allowed Sony to deliver not just a more powerful console, but a quieter one, a more efficient one that stays cool under pressure and performs without compromise. It's the kind of detail most players will never see, and that's exactly the point. The best engineering often hides in plain sight, but here's the thing, liquid metal is also electrically conductive. If it leaks, even in the tiniest droplet, it can short-circuit the motherboard. That's game over for the console. So Sony couldn't just slap some on and call it a day. They needed an entirely new process. They needed robots. Not just any robots. A custom-built robotic arm, equipped with a microscopic sponge barrier system, designed to apply the liquid metal with such precision it can't leak. The arm dispenses just the right amount of liquid metal, spreads it evenly across the surface of the APU, and then seals it in with a foam barrier. It's a surgical process. Most people don't realize this, but if a PlayStation 5 is stored upright for too long, the liquid metal inside can slowly shift and pool unevenly. Over time, that causes overheating, throttling, and performance issues. That's why the robots aren't just designed to apply the liquid metal. They're built to make sure it's placed in a way that will remain stable for years, even if the console moves, even if it's shaken, even if it's flipped. That's only one part of the equation though, because once the APU and liquid metal system are in place, the rest of the machine needs to be built with matching precision. That happens in Kisarazu, Japan, home to a 30-meter-long robotic assembly line capable of producing one PS5 every 30 seconds. The factory is cleaner than a hospital operating room. 32 robotic arms perform the entire process, from motherboard assembly to final packaging. And every move is coordinated with ballet-like timing. No human hands touch the machine during assembly, but human engineers are always watching. They monitor the entire line, ready to intervene if anything strays from perfection. One of the most delicate tasks in the entire process is wiring. Flexible flat cables used to connect parts of the console used to be something only human hands could manage. But today, a 2.2-meter robotic arm does it faster and more precisely than any human ever could. It threads, folds, and places the cables with zero slack, zero waste, and zero error. Then comes the real heart. The massive heatsink and the liquid metal cooling system are mounted on top of the chip, locking in the thermal core. With the internals set, it's time to armor up. The iconic white side panels are injection molded and snapped into place. These aren't just for looks. The texture, the shape, and the vent placement are all designed for airflow, part of a carefully tuned thermal design. Every curve and ridge on the shell exists for a reason. It's built to keep the PS5 cool under pressure. And when that shell clicks in, it's a final seal on one of the most thermally efficient consoles ever made. But before a PS5 can leave the factory, it has to survive what some call the gauntlet. This is a brutal, unforgiving series of automated tests. Every port is checked, every button is pressed, the disk drive is tested, the software is flashed, then the console is powered on, and if a single thing goes wrong, it's pulled from the line. There are no spot checks here. Every single console is tested. That's not typical in electronics manufacturing, but Sony knows the stakes. A failure in the field isn't just bad PR, it's a broken experience for someone who saved up to buy one of these machines, and that's unacceptable. So what happens to the consoles that fail? They don't get shipped. They're analyzed, dissected, sometimes recycled. The margin for error is zero. And that's not a figure of speech. A console with a microscopic flaw in its liquid metal seal could fail 1,000 miles away in someone's home. That's why the robots in Kisarazu don't just build, they protect. All of this leads to a moment that most players never see. Finished, tested, boxed, the PS5s are loaded onto pallets and enter a global logistics network powered by predictive analytics. Ships, planes, trucks, all moving in sync. Sensors track every console. Routes are adjusted in real time to avoid weather, customs delays, or port congestion. Because when Sony does a global launch, they don't mean over a few weeks. They mean one day, one moment. A shared human event where millions of players from Tokyo to Toronto unbox their console together. But all of this, all the robotic precision, the silicon engineering, the thermal mastery, none of it starts with an assembly line. It starts in a room, a meeting, a whiteboard. That's where the lead system architect Mark Cerny begins. Every new console starts with a list of things the previous one couldn't do, a wish list, a backlog. But more importantly, it's in a conversation with the developers, the ones building the games. They say what they need, what held them back, what they want next, and sometimes those meetings are brutal, but that's where the breakthroughs happen. One of the biggest requests? An SSD. Developers had been begging to ditch the rusty, spinning media of hard drives for years. Game data, where models, textures, animations, was being bottlenecked. That's why PS5 uses a custom NVMe SSD with a read speed 5 to 10 times faster than what developers even asked for. That means no more elevator loading screens, no more narrow passageways just to hide background loads. Fast travel that actually is fast, but an SSD that fast needs a matching data pipeline. That's why Sony built a custom I/O architecture with invisible compression. Developers don't even have to manage the data compression or decompression. It's all handled by a dedicated unit in the custom chip. The result? Games are smaller but more detailed. Subnautica dropped from 14 gigabytes to 4 gigabytes. Control, Ultimate Edition, was cut nearly in half. Miles Morales, even with higher resolution assets, ended up smaller on PS5 than PS4. The same level of obsession went into the CPU. 8 Zen 2 cores, not just for better graphics, but for smarter AI, more responsive physics, and richer simulation. In games like Returnal, there are thousands of projectiles on screen at once. In Destruction All-Stars, the vehicle deformation is handled by the CPU in real time. Even though some devs wanted 16 cores, they backed off when told it would shrink the GPU. Because the GPU, that's where the eye candy lives. The PS5 GPU is a customized AMD RDNA 2-chip running at 2.23 GHz with 10 teraflops of compute power. That translates into realistic lighting, detailed skin textures, and subtle facial animations that just weren't possible before. It also supports ray tracing, something that wasn't even high on the wish list because developers didn't think they'd have enough horsepower to use it. But Sony delivered, and at their very first PS5 showcase, 6 games already used it. Ray trace shadows, reflections, global illumination, it's all here. Then there's audio. PS5 includes a dedicated unit for Tempest 3D audio. This isn't just better stereo. It's full spatial audio that creates a feeling of presence, like sound is actually coming from around the player. Rain sounds like it's falling in the room. Footsteps in the distance feel directional, and it doesn't require special headphones. Any stereo set will work. Even the controller, the DualSense, reflects this same philosophy. With adaptive triggers and haptic feedback, players can feel the difference between pulling a bowstring and firing a gun. When a weapon jams in Deathloop, the trigger physically locks. When riding a horse in Ghost of Tsushima, the feel of stone versus mud comes through the vibration. All of these features come together in one seamless experience, but none of it works without that custom robot in Kisarazu, quietly applying a bead of silver liquid metal no bigger than a matchstick head. Because in the end, perfection isn't just about power. It's about the invisible details, the stuff no one sees, the parts that make it feel like the future is in your hands. And that's the real secret. The PS5 is a machine built by machines, but it's made for people. The robots build the console, but it's the human connection, the midnight unboxing, the first button press, the shared moment across time zones that gives the PlayStation 5 its soul. Thanks for watching. For more deep dives into the engineering, design, and storytelling behind What if I told you that one of the most simple-looking gaming consoles on the planet is hiding some of the most advanced engineering we've ever seen in consumer tech? The new Switch 2 doesn't look like a spaceship. It doesn't unfold into a robot, and it's not made of unicorn dust. Yet somehow, Nintendo is asking you to cough up a cool $450 for it, a full 50% more than the original. So, what's going on here? Did they lose their minds? Or did they secretly reinvent how handheld consoles are built from the ground up? Let's step inside the world's most advanced gaming hardware factory and find out. At first glance, the Switch 2 looks almost unchanged. Same iconic shape, same detachable controllers, same overall vibe. It's like seeing your childhood best friend after a glow-up. Familiar, but sharper in all the right places. But under that familiar plastic shell, everything has changed. And the story of why it costs so much more starts with the brain of the machine, its processor. Inside the Switch, 2 lives a chip that would make even high-end laptops jealous. Built by NVIDIA using cutting-edge 4-nanometer technology, it's so densely packed with transistors that it's almost comical. The old Switch's processor was built on a 12-nanometer process with about 2 billion transistors. The new one? Over 15 billion. Imagine cramming the population of Earth twice into a space smaller than your fingernail. That's what we're talking about here. But building something that advanced isn't cheap. Creating a 4-nanometer chip involves extreme ultraviolet light, billion-dollar manufacturing equipment, and clean rooms so sterile they make hospital operating theaters look filthy. Each transistor is smaller than a virus, and they have to be etched into silicon with atomic-level precision. It's mind-boggling science, and it shows on the bill. That tiny brain used to cost Nintendo about $25 to make. Now it's closer to $85 per unit, and that's just one part of the console. Now let's talk about the screen. Most people expected Nintendo to go all in on OLED, since that's the direction tech usually goes. But Nintendo, being Nintendo, zigged where everyone else zagged. They went back to LCD, but not the same LCD from 2017. This is a next-generation panel with full 1080p resolution on a bigger 7.9-inch display, meaning over twice the pixel density of the original. It's also rocking HDR10 support, which makes colors pop and highlights explode off the screen in a way the OLED model never could. How? It's thanks to a quantum dot enhancement layer that lets the display render over 1 billion colors instead of the usual 16 million. But here's where the engineering brilliance really shows. This screen is not only more advanced, it's actually cheaper to produce. At about $35 a unit, it's significantly less than an OLED panel, while still delivering better performance where it matters. And because Nintendo opted for this tech, they could pack in features like 120 Hz refresh rate and variable refresh rate, both of which make gameplay feel smoother and more responsive without sending cost into the stratosphere. It's a classic Nintendo move. Don't chase the shiniest spec sheet, which yet build the smartest one. Then there's the Joy-Con situation. On the surface, they look unchanged, but anyone who's owned a Switch knows the original controllers had one frustrating flaw. Over time, they'd get wobbly, loose, and start feeling like cheap knockoffs. Nintendo was determined to fix that, and their solution is pretty genius. Instead of the old sliding rail system, the Switch 2 uses precision-engineered neodymium magnets to snap the Joy-Cons into place. These aren't fridge magnets, they're rare earth components that have to be aligned within 1/10 of a millimeter, too weak, and the controllers fall off, too strong, and you can't remove them. It's a delicate balance, and every pair is tested for up to 1 million attach-detach cycles. Of course, that level of precision comes at a price. The old attachment mechanism cost around $12 to make. This new magnetic system, roughly $35. But it solves a problem that's haunted the Switch since day one and dramatically improves the feel of the device. The difference might be invisible, but the moment you snap the new controllers on, you feel it. All of this extra power brings a new problem though: heat. The new processor is about twice as powerful as the old one, but it also generates roughly 4 times the heat. And heat is the enemy of handheld consoles. Too much of it, and performance tanks, components degrade, and the system becomes a pocket-sized furnace. So Nintendo had to get creative. Their solution was to borrow technology usually reserved for gaming laptops and high-end graphics cards: a vapor chamber cooling system with copper heat pipes. Inside, a tiny amount of liquid evaporates from the chip's heat, travels through the pipes, and then condenses back into liquid, a continuous cycle that wicks heat away far more efficiently than a basic heat sink ever could. Even the thermal paste that connects the chip to the cooler has to be applied by robotic arms with surgical precision. And every single heat pipe is pressure tested before assembly. It's overkill, but it's necessary, and it's not cheap. The cooling solution alone now costs about $25 per console, compared to just $8 on the original Switch. And then we get to the assembly process, the part most people never think about. Back in 2017, each Switch had to pass 23 quality control checks before leaving the factory. That number has more than doubled. Today, every single Switch 2 goes through 47 different checkpoints, each designed to catch microscopic flaws before they ever reach a customer. Robots handle the delicate steps like placing chips and applying thermal paste, while human technicians inspect for cosmetic defects and subtle assembly issues that machines can't detect. If a unit fails even one of those 47 checks, it's scrapped on the spot. Roughly 8% of all consoles never make it past the factory gates. This perfectionist approach adds about $40 to the manufacturing cost, but Nintendo knows it's worth it. A dead console on store shelves is a PR disaster. A flawless one becomes a household staple for a decade. They'd rather eat the loss on a failed unit than deal with the cost and reputation hit of mass returns later. And that's a big part of why Nintendo products, despite being handled by kids and tossed into backpacks for years, just keep working. Now let's talk numbers, because that $450 price tag doesn't come out of thin air. The original Switch cost Nintendo about $100 to $80 in parts. Today, the Switch 2 costs roughly $265 in materials alone. That's an $85 jump just in raw components. Factor in the more expensive chip, the new display, the upgraded Joy-Cons, the high-end cooling system, and the obsessive quality control, and the total manufacturing cost lands around $310 per unit. That leaves Nintendo with a profit of about $140 per console, slightly higher than before, but not outrageously so. Most of their profits still come from the games, where they make $15 to $20 on every title sold. But the price isn't just about hardware, it's about philosophy. Nintendo doesn't design products the way most tech companies do. They don't chase raw specs, they don't brag about teraflops, and they don't race to be the most powerful. Instead, they obsess over balance. Every engineering decision on the Switch 2, from the chip to the display to the magnets in the Joy-Cons, follows the same guiding principle: give players the best experience possible without compromising portability, battery life, or fun, and that philosophy shapes everything about how this console is built. Take that 4nm chip again. Sure, it's powerful, but Nintendo didn't design it to run the latest AAA PC ports on ultra settings. They built it to deliver incredible performance efficiently. That's why, despite packing over 7 times more transistors, It sips power compared to traditional gaming hardware. It's not about brute force, it's about smart power. That's the kind of engineering that lets you play expansive open-world games on the go without your battery dying before the cutscene ends. And that's where a lot of the price increase really comes from. Invisible improvements, stuff you don't see in spec sheets or marketing slides, things like energy-efficient silicon, advanced power management circuits, and tightly tuned firmware. All of that costs money to develop, years of R&D, testing, and iteration. But the payoff is a console that's more capable without sacrificing the pick-up-and-play magic that made the original Switch so beloved. Then there's the display choice. Going back to LCD instead of sticking with OLED might seem like a step backward, but it's actually a masterclass in cost-benefit engineering. OLED looks amazing, no question, but it's expensive, harder to manufacture at scale, and not great for features like high refresh rates or HDR10 brightness. Nintendo's decision to invest in an advanced LCD with quantum dot tech means they can deliver richer color, higher frame rates, and better dynamic range, all while keeping power consumption lower and cost manageable. It's the kind of nuanced decision that seems simple until you understand just how much thought went into it. And the Joy-Cons? That's another perfect example of Nintendo's design priorities. Most companies would have shrugged off the looseness issue as good enough. After all, the original sold over 130 million units despite it. But Nintendo decided to tackle it head-on. Replacing a $12 sliding rail with a $35 magnetic system is a massive cost jump for something that, on paper, doesn't make the console run any faster. But in reality, it makes the whole experience feel premium. Every time you snap those controllers on, there's a satisfying click. They don't wiggle, they don't drift apart, they just feel right. And that kind of invisible quality, the stuff you can't put a number on, is what builds brand loyalty. Cooling is another area where Nintendo could have easily cut corners. They could have slapped in a slightly bigger heatsink, called it a day, and accepted some throttling under heavy load. But instead, they engineered a full vapor chamber cooling system, something you usually see in $2,000 gaming laptops, and shrunk it down to fit in a portable console. It's over-engineering at its finest, and it's why the Switch 2 can run more powerful games without turning into a space heater. So now the question's on you. Does Nintendo's obsessive approach to engineering justify the premium price? Would you pay more for something built to last and perform this well? Drop your thoughts below and make sure to stick around, because next time we're cracking open the secrets behind another iconic piece of tech and revealing how it's built from the inside out.